Note card 41, linear approximation. So in this video, we are going to use our derivatives to find tangent lines and then use those tangent lines to predict outcomes. So we are approximating, we're predicting around where a point should be based on our derivative. So here we go. So linear approximation is all about using our equation of a tangent line in order to predict where a value is. Okay, so what we're going to do is we're going to find the equation of the tangent line, step one. Then we're going to use that tangent line, we're going to substitute an x value into the tangent line to get an approximate y value. Okay, then this is the part that's a little bit more conceptual here. If the function is concave up, the approximation is an underestimate. Okay, so here's why. If it's concave up, right, if it's facing like this, and I've got a tangent line here, tangent line can only touch once, so it can't be on this side here, it would be going this way, right? So see how my line is underneath my curve here? That means that it would be an underestimate, right? If I'm using my line to predict it, the curve is actually going to be a little bit above my line. So my prediction, which would be on the line here, would be underneath my actual value of my curve. So concave up leads to an underestimate. In the same way, if I have something that's concave down, at that point then my tangent line would be here, and it would be over my curve. So if I'm using the line here on this concave down curve, I would get an overestimate. Okay, so my rule of thumb is always just to draw it out. I just think that's easier than memorizing the rules. I just draw myself a curve, and that way you can very clearly see that in this case it would be an underestimate, in this case it would be an overestimate. Okay, so let's do number one together. So number one gives me this function and says write an equation of the tangent line to f at x equals -2. So that's our normal process that we've been doing. So equation of the tangent line means take the derivative, because I need to find the slope there. It'd be 4x cubed minus 6x, okay? And then I'm finding it at x equals -2. So I want y minus y1 equals m times x minus x1. My x1 they gave to me is -2, so this would be x plus 2. I need to find my m and my y1. Remember, my y1 comes from the original, my m comes from the first derivative. So I'm going to plug in -2 to both of these. I would have 2 times 2 times 2 times 2, which would be 16, and be positive because I have a even exponent. And then minus 3 times 4, so 16 minus 12 would be 4. So y1 would be 4 here. So I'm going to say y minus 4 equals. Then my slope, my m, comes from my derivative. So I would have 4 times -8, and then plugging in -2 plus 12. So I'd have -32 plus 12 would be -20. So that is my slope there. Now it wants me to approximate f of -2.2. So all that means is that I take this equation and I make this x -2.2. So I have y minus 4 equals -20 times -2.2 plus 2. So that would be -20 times -0.2, which would be 0.4. So I have y equals 4.4 because I'm adding that 4 on over there, right? So that is my linear approximation. This example comes from an actual AP exam. It's an open response question. It gives us a table here and says, let f be a function that is differentiable for all real numbers. That means that if it's differentiable, it's also continuous, so we're working with some kind of continuous curve here. The table above shows gives the values of f and its derivative for selective points on the closed interval. The second derivative of s has the property that the second derivative is greater than 0, right? So we know that that means concave up. So I'm just going to make a little note to myself over here so that I remember that that means concave up. That might come in handy later on. Hint, hint. Okay. Now it says write an equation of the line tangent to the graph at f at the point where x equals 1. Okay, so I care about x equals 1. Use this line to approximate the value of f of 1.2. Okay, so I'm going to need to write an equation line using the information given. And then it asks me if the approximation is greater than or less than. So that's where we'll talk about that concave up part here. All right, so I want the equation of a tangent line. So I know I need y minus y1 equals m times x minus x1. x1, I already know, it's 1. Okay, so I'm going to do that. My m, remember, comes from my first derivative. This is nice. We don't actually have to do any calculations. I just have to find it. So I want to look for where x equals 1, and I want my, so the f of x would be the y value, right? So y1 must be -4, so I'd have y plus 4, right? So again, looking at my little chart here, I just looked at 1 and f of x to give me the y value, and then they give me the derivative too. So I don't need to go through the process of finding the derivative and plugging it in. I just know that the derivative is 5, so the slope must be 5, right? Just using your table there, okay? Then I want to find at 1.2, so I'm going to plug in 1.2. So I have y equals 5 times 1.2 minus 1 is 0.2 minus 4. 5 times 0.2 is 1. 1 minus 4 is -3. So my linear approximation is at -3, okay? So now I know that f of 1.2 is equal to -3. I knew that this was concave up, so my tangent line must be below my curve. So then that means that this would be a underestimate, right? My curve is above, this is below, it's an underestimate. So it says, is this approximation greater than or less than the actual value? So it is less, the approximation is less than the actual because f double prime of x is, greater than, concave up, is greater than 0. That's all the justification that you need to put. The AP exam knows that if you are writing that, that means that you understand this whole concept right here. You can always draw the picture just to help yourself out, but this is all the justification that you need. All right, great work today. On to video 42. Now, I miss you guys. Hope you're doing well, and I'll see you soon.